let's get started. Thanks everyone for coming. We are going to talk about building cloud-native apps with Azure Kubernetes Service. And this is level 100, between 100 to 200. At least we are not going to go too much depth of the technology, but we will talk about the concept. So, about me, who am I? My name is Irfan Mohammed. I am Senior Cloud Solution Architect working in Microsoft in the team called Digital and App Innovation team at Microsoft. I have a strong level background. I wrote my first application in my first project of coding assembly level in CSC++. That doesn't have that code that we could have started with early. And used to have my math problems I used to write in C language and we tried to solve there with the C language. So that was my love of something. And then of course I started with Java 4.0 and PHP 2.0 Visual Basic and C++. I did a lot of certifications. I just put few which are relevant, like a lot of Microsoft certifications. I have Microsoft certified trainer as well. I have bunch of Kubernetes certifications, like which are very much interested in the industry, CKD, CKD plus data action administration and many more. You can see the LinkedIn profile. Cool. Alright, so what we're going to talk about today, which is very interesting part. First we will talk about what is cloud native architecture. So we will touch base on the concepts of cloud native architecture. Then we will go in the overview of Azure Kubernetes Services. Then we will talk about how you can implement cloud native architecture into Azure Kubernetes Services, which is very important. And what we want to achieve out of this session today. First of all, we want to have a clear understanding of cloud native architecture. What are the building blocks and pillars of cloud native architecture? It's not a buzzword. It's not like people use it a lot, but it is something that has some patterns and practices. We will talk more about that. We will understand the importance of building cloud native architecture. That means that what are the benefits that organization get building the cloud native architecture. Then we will have the understanding of Azure Kubernetes Services. Then we will learn how to build the cloud native apps using the Azure Kubernetes Service. So these are the outcomes, and hopefully at the end of the session, we will be able to achieve these outcomes. Okay, now let's start with the concept of cloud native architecture. Let's start with this. So traditionally, like in your in a traditional organization, when you are running your workload into on-prem, you have a lot of problems. The problems like you have like a cost problem, you have like long release cycle problem. You have a problem like knowledge, that you have the admins who have the knowledge of deploying infrastructure. Plus, we treat the infrastructure as a pet rather than kettle. There's a concept there. So the point is that you treat the infrastructure as a pet. That means that you have to feed it, you have to keep it running all the time. So these are the problems that we get when we run on-prem. Now, when we move to the cloud, will the cloud solve that problem? Would that solve the problem? It may not. So people tend to think, okay, why not I just lift and shift my application and deploy to container? Right? If I'm running on-prem, why not I deploy to container? That may solve the problem. But in reality, it may not. The other people say, okay, why not we deploy to Kubernetes? Kubernetes will solve my problem. Let's do a deploy the Kubernetes. Because that is the thinking even today, the people mindset is, okay, I am running my container or application on-prem, let's deploy the cloud, let's spin up the Kubernetes cluster and just deploy it. But what's going to happen is, it may end up the cost, you may pay more. You may have more problems in terms of the release cycle and all sort of things. Because what is missing in the piece is this guy, cloud native. That is a piece. What does it mean? Let's look at what the cloud native means. Okay, so cloud native architecture is a concept, it's not a technology, it's a concept, it's a set of guiding principle, and it is principle to design where your set of guiding principle practice to design application to advance your cloud computing model. So what does it mean is it's a pattern, it's a practices that you adopt so that you can deploy your application anywhere. And you are not going to be dependent upon any cloud provider. So what happened, like my experience, like if I'm working with a customer and they say, okay, I am running my workload, I am running my application to Kubernetes cluster onto AWS, let's say. And if I ask, okay, can you deploy to the AWS? You say, no, we can't. Why? Because I am dependent upon so many of technologies with AWS that I can't deploy. What does it imply? It implies that you are not doing the cloud native architecture. Because the principle of cloud native architecture is you can take your application, you can deploy anywhere you want. It can be on-prem, it can be on AWS, GCP or Azure or any cloud which comes in future. It can be deployed anywhere. So that is the main concept of cloud native architecture. Again, it's a set of loosely coupled services. What does it mean is, it's a small services or applications you deploy. Either you containerize it or whatever the cloud provider provides technology you can deploy. But mostly when we talk about the cloud native architecture, we talk about the microservices. So microservices set of loosely coupled services. Loosely coupled means they are not dependent on each other and that can be deployed anywhere you want. So these are the what's called, this is the definition of cloud native architecture. The four things, as I said, set of design principles. Application can be deployed anywhere. There's a good litmus test. If you're designing the application, you should think that can be deployed anywhere, regardless of which cloud provider it is. Set of loosely coupled services and not reliant on any single cloud provider. Now, cloud native versus traditional application architecture. So, these are some of the problems and we face with the traditional and what we find out in the cloud native architecture. For example, unpredictable. The workload of traditional application is unpredictable. That means that we don't know how much memory CPU can use. We talk about the monolith application. It's hard to be scaled, hard to be deployed. But when we talk about the cloud native architecture, it's a predictable workload because we know that we are deploying small independent applications or the microservices. I know that my CPU memory requirement, and I know that when I need to scale, I can scale X number of services anytime they depend on the workload. Again, like a traditional application is OS dependent. The people who come from the on-prem background, who develop on-prem, they know that when we used to develop, we used to use, for example, Windows DLLs or libraries. Our applications were dependent upon them. But when we talk about the cloud native apps, it's OS abstraction. That means your application, either you're doing a .NET or Linux-based application, it should not be dependent upon any of the library. Oversize capacity, that's another problem with the traditional apps, that we oversize. For example, I am running my development application, and I want to deploy it, I give my requirement to the infrastructure team, and say, okay, maybe when the workload grows, I may need 50 VMs at one time. So they will provision 50 VMs for me. And I face this problem, of course, past organization, because I know that maybe Christmas time there will be a load. So they say, okay, let's provision 50 VMs just to provision for that, and most of the time throughout the year, 11 months of the year, those VMs will be idle and you're just paying the cost of that. That's over provision capacity. But with the cloud native architecture, we do the right size capacity. What does it mean? I just run the minimum workload, minimum number of instances, let's say one or two instances, and when the load grows, when the load comes, I can scale based on the demand. Similarly, siloed and collaborative. So cloud traditional is siloed. Siloed means that you are working in a silo. Your development team working in a silo. That means that the team do the complete the coding, they hand over the testing team hand over to the another team, for example, the stress testing team, and then finally hand over to the what's called infrastructure team for deploying the production. So that's all the siloed approach. But when we talk about the cloud native architecture, we talk about the collaborative approach. Then, of course, waterfall is that's again when we just talk about the waterfall approach as well. Silo plus waterfall, and cloud native we talk about the continuous delivery. So continuous delivery, continuously you deliver to the production to the customer. Dependency, there is a dependency cloud and traditional, but cloud native applications are independent because they are loosely coupled applications. They are not dependent upon any other. Think about it when you have a big monolith application in which you have multiple modules in it. All the modules will be dependent upon each other. So that means you can't independently scale or deploy those modules. But when we talk about the microservices, or cloud native architecture, you can these are independently deployable, independently scalable as well. Manual scaling in a cloud, in a traditional world, for example, even if I deploy the VM, that means that in the traditional, even today, the big organizations, big banks, they all just going, they are have this manual scaling approach. That means they are running on-prem and they manually scale. They know that, okay, if they anticipate that maybe Christmas time I will have more workload coming, let's go and add more VMs and deploy the app. But cloud native does not go with that approach. It's just automated scalability. Plus slow recovery in traditional cloud native is a rapid recovery, which is recovery from the failure. So if the application is down, it will immediately bring up another instance and start taking the load. But in traditional work, it's very hard. I mean, it's outages and people just wake up at night. Life is miserable. Okay, so benefits of cloud native architecture. Let's talk about one by one briefly. Business agility, of course. Business agility is that quick to the market to meet the market demand. Because in the digital world, in today's world, you need to be upfront. All businesses need to be upfront. They need to deploy and release releases as soon as possible to meet the demand, customer demand, as well as to go up ahead of the competitors. If they have the release cycle of 6 months, the opportunity is gone. So they have to be quick. They have to be deployed every sprint cycle. For example, that's the ideal situation. Every sprint cycle they should deploy so that they can get the feedback loop, close the feedback loop, and incorporate the changes and deploy quickly. But in the traditional manner, you can't do it. So that is the big benefit that business get with the cloud native architecture, the business agility. And that's the whole idea behind this modernization, containerization, everything. Because at the end of the day, if business is spending millions of dollars, at the end of the day, business will ask what I'm getting out of it. It's business agility, because you can deploy as quickly as possible, get the market benefit, realization of the benefit as quickly as possible. Speed to delivery, of course, this is related to business agility. Speed is very essential. Speed means you can quickly deploy as soon as possible. Compared to the traditional approach, you are deploying a 6-month cycle, 3-month cycle. Safety is very important. That's the benefit we can make, get with this cloud native architecture. Safety means that if you are going fast, you have to go safe as well. You have to drive Ferrari 200, then this has to be, we have to drive safe as well. So safety is important. We will talk about more how we get the safety when we deploy the cloud native architecture. Visibility, of course, you need to know what is happening. You need to understand, be aware of what your application, you deploy that application, is it performing well? And is it meeting the demand? Is it meeting the market demand as well? Do I need to scale it? And do I need to take the proactive action? These are the visibility. Fire isolation, and fault tolerance. These are for the resilient architecture. Isolation means that you have to prevent the cascading failure. So this is about your application architecture. What does it mean is if you're deploying the application, then if the application A or service A is calling B calling C, and if C is down, then that failure should not cascade all the way to B and C. If that happens, your whole system will melt down. So that is one of the benefit of the cloud native architecture is we isolate the failure. And fault tolerance is we tolerate the fault. What does it mean is if the service A is calling service B, then it can tolerate if service C is down, then it can tolerate the downtime of service C. There are techniques, for example, retry, circuit breaker, these are the techniques that we use. Automated recovery from the fault. So that means that in the traditional world, if something goes down, then your server admin infrastructure, your application team, your support team all sit together trying to solve the problem. And there's a call at night, there's a production issue, say one issue, and everybody's on their toe. But when we talk about automated recovery, it recovers on its own. If the application is down, it will recover on its own. So that is the benefit of cloud native architecture. Plus the scaling we just based on there. Scaling means as the load comes, you can scale your application. Now, so these were the benefits. Now, what organization achieve out of this? This is very important. Time to market. We touch base on this. In the traditional world, it's usually 4 to 6 months of release cycle. So time to market. But we talk about the cloud native architecture. it is like a 14 days of a sprint. That means every sprint you deploy to the production. Application team productivity, team dependent upon manual processes, handovers, wait time, multiple wait times. But when we talk about the cloud native world, it's a DevOps team. They control their whole environment, and it increased the 8 times of velocity improvement. Time to start. It usually, like I remember that my time when I used to ask the environment from the like infrastructure, like I am doing development, give me the dev environment. I used to wait 4 to 6 months or weeks easily, and then I say, okay, I need the UAT environment. Just wait 4 to 6 weeks for the UAT. As for another environment, wait for 6 to 6 weeks. When we talk about the cloud native, it's a minute. Application team can go and spin up their own environment. They don't have to wait for infrastructure. Similarly, change frequency in like a traditional approach, 4 to 6 months, overnight, risky deployment at night time, downtime, we create outage window, and then we deploy during that time. If something goes wrong, then we revert back, roll back, those kind of stuff. In the cloud native world, we do the blueprint deployment, which is low risk and you can deploy any time of the day, which is very important. Change risk is very high in the traditional world. Even today, like the businesses which are following this approach, they are aware that risk is very high because during the small change, they have to test the whole system, even for the small change. Time-consuming, costly, and risky deployments. But cloud native, low risk because we deploy the microservices. We have a small services. We know that what this service is doing. I just go and do the change, do the testing, and deploy it. And if anything happens, I can roll back it. And if I'm doing the blueprint deployment, I can roll back it easily. Similarly, like platform reliability, outages, shared point of failure. That means the model approach, the traditional architecture. I have a multiple point of failure. It's not just the application point of failure; it's the infrastructure point of failure. With the VMs and database connection, there's a firewall. A lot of things involved in between. So there are multiple points of failure. But when we talk about the cloud native architecture, we isolate the workload and we deploy the resiliency into the architecture, incorporate the resiliency, but so we mitigate that risk. And of course, when the cost is high, because we just touch based on that, over provision infrastructure means that I pay a lot for the infrastructure, and mostly that infrastructure is idle. The cloud native, it's just a very low footprint of containers we run. Only few containers we run. When the load grows, we can increase the number of containers doing auto scaling. And what the business get out of this at the end is the increase in revenue. With all of this approach, increase in productivity, low risk and low cost. So these business would care about these factors: risk, cost, risk, productivity, and revenue. Revenue is high, cost is low, risk is low, productivity is high. That's what business will achieve at the end of the day. Cool. Now let's talk about how I developed the cloud native architecture. I just said that this is the practices. It's not technology; it's a practice. So how would I do it? Number one, microservices. We will go into some detail about each of that, but let's look at that. 6 pillars of cloud native architecture. Microservices, of course. Everyone loves microservices. 12-factor apps. We'll touch base on 12-factor. Containers, that's another part of building block of it. Agile platform, we'll touch base on that, and when we talk about the AKS, we'll go into more depth of agile platform. Observability is very important, and as if you remember that slide, we shall talk about the benefit of cloud native architecture. I touch base on visibility, so when observability is related to that, plus continuous delivery. It's not a continuous deployment, it's a continuous delivery. We will talk about that in more detail. So it's continuous delivery, continuously deliver to the production, to the end user, to the customer, continuously deliver. Let's talk about each of that. So microservices, a lot of definition exists of microservices, but the most simple one and common one is Sam Newman, I think 2009 or something, he wrote his book, and he said that set of loosely coupled services which does one thing and one thing well. What does it mean? It's a single responsibility principle is talking about. They do only one thing, microservices. For example, if I have order management domain and I have order, payment, shipment, for example, so each service responsible for doing its work will do its work only. That means order taking service is responsible for taking the order only, on the shipment. It will take the order and then publish the event, for example. Then shipment service does what it has to do. So they run on their own processes, communicate via the API, independently deployable, use coupled service that does multiple. So independently deployable, that means that I can deploy microservice independently regardless of what other service is doing. That means my service or other services should not be dependent on each other. It's very hard to achieve, to be honest, because a lot of people design microservices, and because everyone does microservice, but at the end of the day, it's called micro-monolith service, becomes micro-monolith service. Because we are so much, used to doing the monolith application that we tend to do everything into the one service rather than thinking about doing fall in the single responsibility principle. Build around business capability and value dependent deployable. So what does it mean is that they build around the business capability, and the best design model of that is to be the domain-driven design, in which you do the domain, design the domain, define the business boundary context, and build the services around the boundary context. And they enable speed, safety, and scaling. Remember, we talk about the speed, the benefit cloud native architecture. This is how this is the benefit you're gonna get the speed to market, because you have small services you can deploy anytime you want. Safety, of course, and scaling. You can scale anytime you want. So this is the one of the building block of out of 6. I have 6 at the top. First one we discussed. 12-factor app. So these are the principle of building the application, cloud native application, and that was, I think, the developer in Azure Kubernetes, I don't remember the year that he put together these principles. Let's touch base individually on each of that. So code base means that each service should have its own code base. That means that the services should not share the code base. If I have a product service, order service, and shipment service, so there should be separate repo for each of that. I should not have the one big repo and I have maybe separate module for each of that. That defeats the purpose. I should have a separate repo, and that repo would have its own pipeline, deployment pipeline, using the CI/CD approach or something. But it should be, the idea is that I should have the separate repo for each of the service. Dependency means that I should not incorporate dependency within my service. If there is a dependency, that I should externalize that dependency. So in Java we use like a thing called Maven packages or Gradle packages. .NET where we use NuGet, or Node.js we use a thing called NPM package. So things like that we externalize the dependency. Config means that we should not incorporate or store the config within the code. Traditionally, even when I used to develop a long time ago, I just used the constant, I just put the value in the constant. That defeats the purpose. We should not put the configuration of the code. Similarly, I should not store the configuration within the code. So, for example, if I have an ASP.NET application, web.config, I just store all the config in web.config, I just do the check into the repository, that also defeats the purpose. Because when I deploy, I should be able to deploy the config separately, so that the code is separate, the config is separate, I can go and do the config changes anytime. So that is externalizing the config. Backend services, it means that my code should not be dependent upon the backend service. If let's say if I'm using the SQL database on my local, then I should use the config to connect to that database. So if I deploy to the cloud, I just change the config, I should be able to connect to the database. It should not be tightly bound to the backend services. Build, release, and run. That means that I should have a separate process for building the code. That means if I do the Docker build, create the image, and push the image to the container registry. That's the build part. Release part means that I should have a separate release cycle or pipeline to release the code, and run is that I have a separate process to run the code. So these three things should not be tied together. Processes is that the services should be deployed by independent processes so that I can scale those processes separately. For example, if I talk about Docker containers, those are separate processes. I deploy my application as separate processes, and then I can individually scale up and scale down those processes or the containers. Port binding means that my application should be listening on a particular port, actually exposing the port to listen to the incoming traffic. Usually we do in a Docker container. When I expose my application, I define that this is the port number that the application will be listening on. Concurrency is the scaling, that my application should be able to scale up and down anytime. Disposability means that the application can be disposed at any time by the platform. So it should not misbehave when it gets disposed. In the Docker world, in the container, in the Kubernetes world, let's say if there's not enough resources and the container is a low priority container, then the Kubernetes sends a signal to that pod to kill that pod, to clear the resources. So in that instance, I should design the applications so that whatever it is doing, it should complete its work when it gets the kill signal. That's what it does. Otherwise, if your application doing some important work, it gets the kill signal, it may leave the database in inconsistent state, or your whole system in the inconsistent state. So you should design a system in such a way that when you get the kill message from the operating system or from the platform, it should be able to dispose nicely. That's what the disposability means. And then prod parity, this is very important, especially people who come from the old world or on-prem world. They know that I deploy my application on dev, working nicely, everything is working. When I deploy to production, it's not working at all. And I seriously spend my nights and nights just solving the production issues. I used to go to the office at night time just for the deployment because it was working in dev so nicely. Working on UAT or perfectly working on UAT, but it's not working in production just because that is just one beauty configuration or some like IS or something, or just a patch was not there. This happens, So cloud native and the 12 factor saying that it should minimize the dev and production parity. There should be minimum parity, and we will talk about that in more detail. We will talk about the AKS and logs. Of course, it means that your application should not be attempting to write its log into the file. It should be doing std out and std error to the console, and then the platform should be responsible to collect that log and send wherever it has to. And admin processes mean that when I start up my application, it should not do any of the admin process, any of the bootstrapping work. I should externalize that bootstrapping work into the separate process. So Kubernetes provides for example, like a job, clone job I can run there, or I can run the init container as well. But my application should not be doing those kind of stuff. That's what the admin process means. Let's move on. Container. Alright, so if I say container is a lightweight VM, most of the people will throw me out of the window. That's not a lightweight VM actually. So, what it is, it's an evolution, where we traditionally used to deploy onto the bare metal. I remember my time, I'm not that old, but I still remember because I worked for a lot of organization that was a traditional organization. They used to deploy the bare metal, but it means it's just hardware, it's an operating system, and I IS running on there, and I just deploy web services or web apps onto that IIS. So one IIS would be hosting 10 websites or web applications. It's running on one server. I come from that actually. Then there was a revolution, then we moved to the VM. Then what it means is I have hardware, I have operating system, then there's a hypervisor, then that gives me multiple VM. I can go and deploy an app to multiple VMs. That gives me more flexibility so that I can have, let's say for web-facing app, I have a separate VM, for backend apps, I have a separate VM. But that does not solve the problem being a cloud native because there's a high startup time of these VMs as well. What if let's say I deploy the app, for example, scaling as well. There's high startup time. If I need to scale this VM, I need to add more VMs into it. Startup times, this VM typically take 5 to 6 minutes or maybe more. Then application will take its own time, so it defeats the purpose of cloud native architecture because it needs to respond quickly when the load increase. Then we have the containerization, which is hardware, and then I have operating system running on top of that. Then I have a container runtime on that operating system, and I run the multiple containers on top of that. And on that container, it provides its own binary and the runtime, and then I can host my application to the container. All good. but that does not solve the problem. We will talk about more, because talking about individual containers is fine, I mean, for the non-production workload, but what about the observability, automated recovery and scaling, all sort of things? Who is going to go and do this kind of stuff? So that does not solve the problem. Yes, at one end it does. Yeah, I can just lift and shift and deploy the container, but that's not for the production. So now let's touch base on to the next pillar, Agile platform. It provides a self-service abstraction from web API. So Agile platform means that it is the platform that I can use. It provides the APIs I can use to not only deploy my application, but also to perform the operations like scaling my application. It provides observability. It provides a self-service way of doing this stuff, rather than I go dependent upon the infrastructure admin person for my application deployment. I should be able to use that in a self-service manner. And also, it helps me to simply push the code in the form of pre-built. For example, if I have a Docker image, I should give that image to the platform, and the platform should take care of deploying that, rather than me going and telling the platform, go and deploy to this VM or that VM. That's the Agile platform. Plus, team don't have to think about where the code is running. That's very important, because all they care about is the application team is give the code to the platform, and platform should take care of deploying the code, regardless of where it is running. And of course, should provide the scaling, scheduling, failover, scaling, automated updates, and other stuff. That's the Agile platform. Traditional one does not provide the Agile platform, because if I deploy the bare metal or deploy the VM, it does not provide the Agile platform, because I am dependent upon the infrastructure admin. Next one is observability. This is like fifth pillar. So critical application need end-to-end monitoring. This is very important, because if you deploy the application and if you don't monitor it, that defeats the purpose of being the cloud native, as well as having the visibility and taking the proactive action. So you should have the mechanism not only take the proactive, but also the reactive actions. The proactive means that something happens, before something happens, you know something's going to happen, and then you take the proactive action to rectify that. Similarly, if something happens, then you should have the mechanism to take reactive action in an automated way. For example, if I'm getting a load in my application, right? I can't have the admin sitting all the 24/7 just looking at my application load, and if the load increases, go manually scale that application. It can't happen. So the reactive approach would be that I should have some mechanism which will go and look at my load, and if the load increases, it should scale my application. So that is the reactive approach. Similarly, if the error happens, for example, error record of the application, I should have a workbook or something which run automatically and rectify the error. So that is the reactive approach. And those complex system require complex distributed system require end-to-end monitoring. For example, if you have hundreds of microservices running in your platform, and one service calling another service, then you should have a mechanism for the monitoring end-to-end. Otherwise, manual monitoring is not possible. And we talk about the productive approach. Now let's look at the next one, continuous delivery. So, in cloud native world, teams should deploy frequently to achieve business agility. So this is continuous delivery, not continuous deployment. When we talk about the continuous deployment, it means we deploy the production continuously. But what does it mean? We have a stop gate, and we wait for somebody to approve the change request, then that gets deployed, right? But in the continuous delivery world, ideally, when my developer checking the code, it should run the automated pipeline, all sort of stuff, and deploy the code. Yes, if I don't want to launch to the public, to the customer, I can use the feature flag, for example. But I deploy end-to-end. I should not have any stage gates in between. That's the continuous delivery. Automated feedback loop, so accelerate automated feedback loop. So this is very important. So if I deploy continuously to the production, and so what it will help me is to get the continuous feedback loop. But that is very important, because if I deploy every 3 months, and after 3 months I get the feedback from the customer, I go incorporate that feedback, another 3 months our customer have to wait, and then deploy that to defeat the purpose. So continuous delivery will shorten the feedback loop, and speed to the market. And usually we can implement the form of CI/CD pipeline, which is called continuous integration, continuous delivery. And so this is just a way of I have two pipelines here. One is the development pipeline, and one is the what's called infrastructure as a code pipeline. So if I commit the code to the version control, it will kickstart the build. It will run the automated test in the form of unit test, functional test, integration test, performance test testing. Then I have a security test. So this is like the kind of DevSecOps pipeline. I have a security test. I can do the code analysis, vulnerability scanning, image scanning, penetration testing, all in an automated manner. Everything is fine. I go and deploy and go to production in the CD pipeline. Similarly, in the you have an infrastructure as a code. For example, I'm deploying AKS cluster, for example. So I commit the code, it does the build, validate automation, deploy infrastructure. It tests the infrastructure to make sure that everything is okay, and then go and deploy to the production. So this is just a sample of how you can do. Okay, so now I have a second part of the presentation, which is overview of Azure Kubernetes Service. So we covered first part, which was cloud native architecture. I'm sure everybody would have good understanding of cloud native architecture. Next one is just a high level overview of Azure Kubernetes Services. And our third part will be how we can implement the cloud native architecture, which we saw in the first part, onto the Azure Kubernetes Service, or how AKS help us to implement the cloud native architecture. Moving on, so AKS is a service, Kubernetes service developed by Microsoft. It's a PaaS service. It's highly integrated service because it integrates with a bunch of Azure services like ACR, Azure Test, Share, File Share, Azure SQL, Key Vault, and many more services. This is just a high-level architecture of Azure AKS. So you can see that just a deployment of microservice on AKS. So I have another slide to go into more detail of it, but just this slide is showing that what AKS is. It's a PaaS service and which is highly integrated with a bunch of other Azure services. It's a managed Kubernetes cluster. We'll talk about more what does it mean, but what it provides, what feature it provides. So it deploy and manage Kubernetes with ease. So you don't have to worry about the Kubernetes deployment, version upgrades, patching, all sort of things, because it's a managed service. So you can just deploy and manage with ease. So management is very easy because it's a managed service. Scale an application with confidence. Secure your Kubernetes environment, provides a secure environment, of course, in form of RBAC, Azure RBAC, and AD controls and other stuff. Accelerate containerized application development, because teams don't have to worry about the infrastructure management. All teams have to worry about is their application. So they focus on their application, and the AKS takes care of all the back-end infrastructure heavy stuff. How you want to, okay, so this is like also, it works with a lot of open source components and tooling, and you can set up CI/CD with the click of buttons. So the CI/CD templates available, you can just use those templates, the click of button, you can deploy your application using the CI/CD templates. Okay, so this is like what Microsoft provides and what customer, difference between the like a DIY Kubernetes and managed Kubernetes, and what is the Microsoft responsibility. So you can see things here. This is the Kubernetes architecture, by the way. So this is the control plane which manages Microsoft, which Microsoft manages. This part is the customer VM part, which gets deployed into a customer subscription in the form of nodes. So only nodes gets deployed into the customer subscription, and that nodes run the pods. Can deploy multiple nodes, and then each node can run multiple pods. Things here, this side is, you can see the DIY means that you just do your own Kubernetes, and you can deploy your Kubernetes anywhere, cluster. You can deploy bare metal, or you can deploy any cloud provider. You can just spin a bunch of VMs and deploy the Kubernetes. But the difference, this is showing the difference between a DIY Kubernetes and Microsoft managed Kubernetes. So the containerization is, in the DIY, containerization is your own responsibility. In the AKS versus shared responsibility, the containerization, plus application, iteration, debugging is a shared responsibility. CI/CD is against shared responsibility. DIY is on your own. Provisioning, like a node provisioning, updates and patching is purely Microsoft responsibility. And this is the most time-consuming part of the admins, because they have to provision the cluster, upgrade the cluster, add the nodes to the cluster, add the patches to the cluster, plus upgrade the Kubernetes version. These are very time-consuming exercise. Here, Microsoft is all managed by Microsoft. Reliability and availability is Microsoft responsibility. If you are doing your own Kubernetes, that means you have to manage the reliability and availability of your cluster. Scaling, fully Microsoft responsible. DIY your own. Monitoring and logging, fully Microsoft responsible. So you can see that out of this, top 3 is the shared responsibility and rest is Microsoft responsibility. And top 3 is containerization, application iteration and debugging, and CI/CD. It's a shared responsibility like this. And rest is Microsoft responsibility, which is the heavy part, to be honest. Provisioning, upgrade, patching, reliability, availability is not easy. It requires a lot of infrastructure plus cost and other stuff. Scaling is Microsoft responsibility, monitoring and logging again. Because monitoring is not an easy part. I will touch base on monitoring when we go to those slides. Let's move on. So cluster architecture, this is again like another just pictorial view. So customer managed part and Microsoft managed part, or Azure managed part. So the control plane, which has API server, scheduler, control manager, etc. database, is all managed by Microsoft. Only thing which is at the customer side is the node. And the node, this part gets deployed automatically, like a kubelet, kube proxy, container runtime. Only thing that customer deploy is their containers. Node patching and upgrade is also Microsoft responsibility, and you can do the auto upgrade as well. Even the Kubernetes version of auto upgrade, you can opt for the auto upgrade as well. Additional benefit is a free, pay as a free service actually. Pay only for the worker node in the cluster, not for the master. Free for the master node, not for the worker, of course. So, you see how many components were there in the master node. So, heaps of components. All are free. You only pay for the worker node. So, that reduced your bill too much. Drastically. If you deploy your own cluster, that means you have to spin up the VM for the master node and you have to pay for that. Here, all you are paying is just for the worker node. So that means if you have a 10 worker node, you are only paying for 10. If you reduce your workload to 5, you pay for 5. Management of a service through the Azure portal is easy, CNCF certified, and it's a compliant. So SOC, ISO, PSI, DSS, HIPAA, and a lot of other compliance. There's a long list of compliance if you go to the website. I just put few here. So that covered the second part of the presentation. Hopefully you should be able to cover an hour, 15 minutes. How AKS support cloud native apps. So we talk about what the cloud native apps is, what are the best practices, what are the 6 pillars of cloud native. How can I use AKS to help me? What AKS will help me to build this cloud native app? So let's see that. Let's talk about the 12 factor. Microservice I did not tell because it's your development practice. So AKS can't help you doing the microservices. You don't go develop the microservices, following the best practices, follow the domain-driven design. Once you develop that, follow the 12 factor principle as well. So now let's map this for 12 factor principle with the AKS or Azure services. I have this slide is for mapping, so code base, code wrapper Azure DevOps for each microservice, package the microservice the image and push them to ACR. So that is the service that you can use. So you can use Azure DevOps for code repo or GitHub repo. Then you can use, when you package, you package and containerize and push those to the Azure Container Registry. And then from there you push deploy to the AKS cluster. Dependencies in the form of when you deploy and when you run you package your image, all the dependencies gets binded into your image and then get deployed to the ACR. Config, you have a config level secrets that is provided by the AKS cluster. So that means that you externalize your config, which is one of the main principles of the cloud architecture, to externalize the configuration. So you externalize the configuration in configs, in the config map. So config map is a resource within the AKS that you can use that, and as well as the secrets. Now, other thing that on top of that, which is very important, that secrets you can store in a key vault. So you don't have to create like a secret object within the Kubernetes and store secrets in a base 64 string. All you do is store in a Azure Key Vault your secret, and there's a the Key Vault CSI plugin will at runtime, which it will inject your secret from the Key Vault into your container. So you don't have to manually create the secrets. Backend services, a test service such as the SQL, Cosmos at runtime, store config in a config map secret, build, release, and run. So build and package your code using a container image and push to ECR. That is the build part. So when you do the build, you package your image and store it to ECR. That finished the build part. The release part is deploy your code to AKS cluster using the deployment chart. Use release, pipeline to the manage release, and tag the release with the build number. So what it means is they'll use Azure DevOps to build the pipeline, and when you deploy your code, you use the build number, tag your image with that build number, and when you deploy, pass that build number to Helm chart, and then it will pick up that image with that build number, and you deploy to the ACR, to the AKS cluster. I have one diagram I will show in a moment. Run, of course, when you run your application in isolated container environment, a pod, AKS container. So what AKS does is, when it not only run your container, but also monitor that the container is running. Sorry, pod is running. If pod is not running, then it will go and spin up another pod. Or if the pod is not healthy, it continuously monitors the health of the pod. If pod is not healthy, it will kill the pod and spin up the new pod. So this is the continuous monitoring. Plus, it constantly monitors the desired and the current state. So what does it mean is, if I have 3 pods running and I define my desired state to be 5 pods, for example, and if the Kubernetes find out that there is a mismatch, there is a desired was 5, running is 3, it will spin up 2 more pods. So to match the desired and the current state. This is what the scheduler does, one of the jobs, to match the desired and the current state. And process, of course, like application run isolated process in the pod. So this is how the AKS support, that you run the isolated processes within the pod. So the pod is in itself an isolated process, and it runs on its own, uses its own memory and CPU, and 2 pods don't interfere with each other. And you can independently scale those processes or pods. Port binding, application running on container, this is a well-defined ports. Use service to route traffic to the pods. So, yep. So what it means is that your container will be defining that I listen on this port, in this port. But when you route the traffic, you use services within the AKS and route the traffic using the services. So this is how you will do it. Or you can use the ingress controller as well to route the traffic to the particular pod, and the pod will route the traffic to the particular container running inside the pod. Concurrency, AKS support that in the form of cluster autoscaler. Cluster autoscaler means that if you have let's say 5 nodes running and you have more pods waiting to be scheduled, then what it will do is it will add more nodes to the cluster. Similarly, if the load gets down, it will see that the more nodes are idle, then it will spin down the nodes, spin down the cluster and remove the nodes. So this is auto-scaling. Automatically grow the number of nodes and cluster and automatically shrink the cluster as well. That is a cluster auto-scaling that is provided out of the box. You just need to turn it on. Horizontal pod autoscaler and VPA. Horizontal pod autoscaler means that you can horizontally scale pod. Horizontally means you can add multiple pods when the load grows. And VPA means vertical pod autoscaler means that you can increase the CPU and memory count. For example, if I am running my batch process, so initially when I deploy my application, and that application needs let's say 10 MI, for example, but when it is running the batch process, it is consuming 100 MI, for example. So what's going to happen is, if Kubernetes find out that this application pod is taking over, it will correct that. So vertical port autoscaler constantly monitor the current usage of memory and CPU, and it will then automatically increase your CPU and memory requirement for a particular pod. So it will get those more memory and CPU portion. Similarly, if the load goes down, it will reduce the memory CPU requirement. So this is what the vertical port autoscaler is. Concurrency, we'll talk about that. Disposability, we have a readiness aliveness pod in Kubernetes, so you use that to check the readiness and liveness of the application. If the application is not ready, then Kubernetes will go and kill the pod, and it will start the new pod. Dev and pod parity, this is you achieve using the CI/CD pipeline when you deploy a cluster. So ideally, you should have the one pipeline which will deploy to dev, production, or UAT, whatever is not anywhere. So you should not go to the portal and do the manual deployment. You should have one pipeline with like a Terraform script or bicep template, bicep script. Use those scripts and just change the config to deploy to dev, or UAT, or SIT, or production environment. So this is how you will reduce the parity, dev and production parity, by using the CI/CD pipeline and the IAC template, by Terraform or bicep template. Now logs. So in the Kubernetes environment, like especially the AKS, there's a thing called container inside. So the container inside collects the logs and send it to log analytics workspace. So all the logs that that application spit out in the form of std error and std out, the container inside will collect those logs and send to the container inside, where we can do more analytics on the log. On top of that, container inside also look at the metrics as well, application metrics, and you can visualize those. I have a slide, we can see that, we will see in a moment that what you can see visually. An admin process, of course, one of processes, the bootstrap scripts or something, then you can run the things called job in Kubernetes. So you can run like a clone job, or you can have the init container. So this is how you can do the 12-factor app within the AKS container. So creating the container is easy. You just do the Docker file, build a container image, do the Docker run command to start the container. It's very easy. You can do all in one. Like even when you build your code, it will build. You can just build the code image when you build the code. It's very easy. But problem starts when you deploy. How you deploy it? How you do when you're gonna do the configuration, scheduling, container availability, resource allocation, load balancing of traffic, monitoring, security, those kind of stuff. Because running the individual container is easy, but when you are going to productionize it, it's not easy, because I need to take care of these concerns of container deployment. So what I need is, I need the things like scheduling. Scheduling means that where do I deploy this container? Like I give the platform, but how would I deploy it? Like which node or which VM I go and deploy this container? Affinity and anti-affinity means that should I deploy to that node, or should I deploy to this VM or that VM, or say that this container should be deployed to this VM but should not be deployed to other VM. So that's affinity and anti-affinity. So if I have the requirement, then how would I control that affinity and anti-affinity if I just go and deploy on my own? Similarly, health monitoring of the container, failover if the container is down, then what's going to happen, scaling, networking, service discovery, and coordinated application upgrades. So these are some of the concerns that get solved. These are some of the elements of the orchestration that individual, I cannot solve all of this on my own. So that means I need some sort of orchestration platform. This is what AKS supports us. AKS provides us the orchestration platform in the form of Kubernetes platform, which covers all of this concern. Agile platform. So let's look at the definition. Let's apply the definition of agile platform we saw in the module 1, or the first section of the presentation. Let's apply that concept here and see how AKS can help that. So this is the microservice architecture in AKS. Very simple. Like I have a client application deployed. I have an Azure load balancer. I have an ingress controller in it, and then I deploy the pod. I do the scaling of the pod, like whenever the load comes, and these are the backing services I have, which gets attached to it. Like I have a cluster, I have Active Directory, like which for the rollback access control. I have Azure Monitoring, which is for the monitoring observability, and I have Azure Key Vault for storing the secrets. Then I have Azure Pipeline for CI/CD pipeline, and then I go and deploy, push my image to the container registry, and I go and deploy. Then it will pull the image from the container registry and deploy the Kubernetes cluster. So this is a simple microservice architecture in AKS. Some of the features of AKS, this again relating to cloud native architecture definition of agile platform. So what it is: managed Kubernetes, automated cluster upgrades, high availability with multi-AZ support. So there's a multi-AZ concept in the Kubernetes, in the AKS world, and it provides a high availability. Scalability, advanced identity access management, end-to-end observability. This is very important. I will touch base on observability in a moment, but this provides end-to-end observability. Deployment pooling integration. This is like the developer pooling integration from your IDE all the way to the AKS. So you can deploy from your IDE, right from your code. When you build from your code, you can deploy to the cluster. That developer integration is available. GitHub actions are available, like some templated GitHub actions. You can just go and use it. It provides the storage, manages storage, advanced networking. The 3 or 4 types of networking you can use. End-to-end developer productivity with CI/CD pipeline logging and automated node maintenance. Automated rollbacks, rollout and rollbacks, service discovery and load balancing, storage orchestration, self-healing, secret config management, batch execution, auto-scaling, IPv4, IP6 dual stack networking, node auto provisioning, and lots and lots of more. Some of the features I've mentioned here. All of these support cloud native architecture. All of these features. Another feature of cloud native architecture, if you remember the definition, self-service API. APIs. It should provide the platform in the form of API. So you get the API. So this is like the Kubernetes cluster. I have this master node, and I have like a worker nodes here. How would I interact with the master node? I have API server here, and AKS provide your API like a REST call to the API server. So the REST APIs are available through which I can interact with the API server. So I can make the REST call for the deployment. For example, this sample is just the get REST call to get the list of pods. Similarly, I can pass the deployment file or deployment config in a JSON to call the APIs to deploy that. So this is one of the feature of the self-service platform, that provide the platform in the form of APIs. It is simple to use kubectl or kubectl. Some people say kubectl. I call it kubectl. Some people say kubectl. But this is the command line tool which actually wrap up the API calls, HTTP calls or REST API calls. So you just do the command line. For example, kubectl get pods. It will do the same thing as you can see in here. So it just hide this call, and it will just make a call to the API server. Of course, you need to log into the API server, make a connection, and once it is done, then you can just do kubectl get pods, kubectl apply -f or a deployment file. You can do that as well. So some of the common commands that I put in here, most common is the get, of course. Example, kubectl get nodes. Applies the most common, another common one. Example is kubectl kubectl apply -f, deploy your deployment file. It could be anything, This is very generic command, apply, and you can pass any YAML file. Of course, that should be very YAML file. It should be creating value resources. It could be either create pod, or it could be namespace, or it could be deployment itself, or stateful set, or it could be service account, anything. It's very generic, so you can just do the apply. Similarly, to get the logs, you say do kubectl logs, the pod and -c the container. You can see the container level logs as well. And exec command is just to get the bash to date. If you want to just log into the container and see for troubleshooting, you can run this command. So just purpose of showing this is that the platform provides API and the command line to interact with the platform. Similarly, this is the kubectl, but there's a AZCLI command as well. AZSER, actually did not put it here, but you can use the AZ command line tool as well to create the cluster. For example, AZ create cluster, it will create cluster for you. Just pass some parameters and it will create cluster for you. So the platform provides the CLI to interact with the platform and create the resources. Autoscaler, we talked about that. So this is the cluster autoscaler. What it does is that it adds the nodes. So when it needs to scale out, it adds the nodes to the cluster if the load grows. So this is what the cluster autoscaler is. And similarly, when the demand goes down, it will remove the nodes from the cluster to save your cost. So that means your admin does not have to wake up at night and just go and add the nodes manually. All it can happen automatically based on the load. Vertical autoscaler, vertical pod autoscaler, we talked about that. This is again when the load, if your pod needs more resources in the form of CPU or memory, then VPA, short for VPA, vertical pod autoscaler, it will change the definition of the pod and it will add, it will specify the memory CPU requirement for that particular pod, and Kubernetes will respect that. It will increase the memory CPU limits. That's the vertical scaling. Similarly, horizontal scaling, this is how it works. So you have a metric server. You define your requirement. Actually, you define requirement here. A metric server collect the metrics of your pod in the form of CPU and memory utilization. Then you have a horizontal pod autoscaler, and it connects to the metric server using the metrics API. And if you define, let's say, if my CPU goes, or if a memory, let's say, goes about 80%, then go is given 2 more pods, for example. So that's the configuration I did do at the HPA level. So HPA will know that configuration, but it will continuously monitor the metric server for your pod metrics. Collect the metrics, and it will just change the deployment. So if you do the deployment, remember that it was at the deployment level, not at the pod level. So if you do the pod resource, deploy the pod resource will not happen. You need to deploy the deployment resource for it to work. So what it will do is, let's say I have like a defined, I have a deployment, and that deployment I have 2 replicas or 2 instances running, which is the pod number of pods. But if I say that, okay, if the memory utilization goes above 80%, go and 2 more pods. So what we will do is, it will just change the deployment and increase the replica set, number of replicas. So what will happen is, that definition will go into its etcd database, and scheduler will go and find out, okay, there is a mismatch in the desired pod and the desired state and running state, and it will go speed up more pods. Similarly, it goes in the reverse order as well. Like if the utilization goes down, then it will go and spin down the number of pods. Now, CADA is on top of that. So what CADA is? So in the previous slide, we only look at this metric server. So this is within the Kubernetes platform, this metric server. It is collecting the CPU and memory utilization of the pod within the cluster. But what if you have the, like, for example, event-driven application in which you have application which is looking at the service bus, for example, right? And you have a pattern that as the number of messages grows, you add more consumers so that you can quickly finish up the number of messages in a service bus. If you have only 2 messages, 2 pod running, then you may have a problem because the queue gets split up, and those 2 may not have time to finish up the all messages. So what CADA will do is, CADA is like event-driven autoscaling. So this is, what it will do is, you define the service bus as the one of the CADA event resource. So what it will do is, it will go and inspect the number of messages in the service bus queue and add number of pods based on your definition. So if you are saying that if my queue has, let's say, 60%, if or 40% left or 60% full, then go ahead and spin up 3 more pods. It will do it for you. That's the concept of CADA. So how it works is, okay, these are number of scalars at the moment available, and the list is growing actually. So I give the example of service bus, just somewhere here, but you can see that the AWS things are here, Azure, IBM, and a lot of other. Even though it is based on, look at the RabbitMQ, Redis Cache, MySQL, a lot of other. Depending upon application requirement, how you want your application to create like to grow the number of pods. The way it works is similar to the previous diagram we saw for HPA. Similar to that, it still have this HPA behind the scene. This HPA controls this whole scaling. But here HPA, look at the metric API. That metric API is now connected to the CADA scaler, and the CADA scaler is connected to the external source. So that in our example, external source is service bus, for example. So the service bus will tell CADA scaler to add more pods. So what it will do is, it will tell to the HPA, and HPA will go and change the deployment file, and it will add more pods. So this is how it will work. Very simple.
So when this CADA scaling happens, it overrides the original native Kubernetes script.
Yes, in that case, either you use CADA or you use Kubernetes own scaling. So if you are doing memory based, you either use that one or other one, because it depends on your application. If your application is consuming the messages from the queue, in that case, the CPU memory utilization will not help you. So in that case, you would not define that, and you will go and use this external source. And that you do all your configuration at this level, CADA scaler level, and the scaler will know that it will go and inspect the external source, and if the number of messages increase in the service bus, it will tell HPA to increase the number of pods. Okay, secret management. This is again one of the concept of, remember, cloud native architecture. So we are just trying to relate those concepts here into AKS. So we have things called secret and secret management here. So I touched base on that. The secret, there's a secret object in Kubernetes. You use that secret object, but the beauty of AKS is that we don't have to store secret in a secret object in Kubernetes. You store that secret into the key vault, the Azure key vault, and at runtime you use like a CSI plugin, key vault CSI, and that CSI will go and inject those secrets from key vault to your secret store, and that will be provided to your cluster container at runtime. So that will add more security controls in your cluster. Now let's talk about the observability. I talk about the end-to-end observability. This is very important concept. So when we talk about the Kubernetes cluster, we need to monitor it end-to-end. There are 5 layers of observability. One is the network level. Right at the bottom, we need to observe what is happening at the network level. I'm just all talking about the Kubernetes in the Kubernetes context. Network in general, you will have the network administrator who will be monitoring your network. But is he monitoring your network from the Kubernetes engine? That means I have these number of nodes. Can these nodes communicate with each other? What sort of packet they are sending to each other? Those kind of monitoring, they may not be doing. Your network administrator, they may not be doing that. So you need that level of networking, monitoring at the network level. Plus cluster components, which is the virtual machine scale set, abstract nodes and node pools. So you have a VMs, again in the context of AKS, those VMs, are those VMs healthy? I have like a virtual machine scale set defined, or I have a node pool defined. How is it behaving? Like And if the autoscaler is on, how autoscaler is working, is it behaving correctly or as I defined or not? Those kind of monitoring you need to do. Plus manage cluster components, which is the Kubernetes own component. API server, XL database, API server, controller manager, the availability of those components, these kind of things, then you need to have the observability. Plus Kubernetes object and workload, which is the deployments, container, replica set, which is the Kubernetes component. Then you need to have visibility that when you do the deployment, what was the status of the last deployment? Was that successful? How long did it take? Those kind of things you need to be aware of. Then you have application level visibility or observability, which is how your application is behaving, end to end. If you have 5 containers running or 5 microservices, then you need to have some sort of end-to-end monitoring, which is called distributed tracing. You need to have some mechanism to monitor those. Generally, what an organization does is they have, I'm talking about the big organizations here. They don't do this network level. They're saying, okay, our network admin is doing that. When you talk about a network engineer, they're saying, we have networking monitoring, but we don't go to the cluster level. We have what's called generic or general level of observability, not specific for the cluster or not specific for the Kubernetes. Similarly, cluster level components is some have, some does not have. Most of the organization does not have this cluster component, does not have an object, their application. So some have application, some have cluster level. But these three, 1, 2, or then the last one, network level, they don't have that. I'm talking about the big organizations, they don't care a little bit about that. So, what AKS provides in terms of monitoring? Here, there's a monitoring solution. For network level, there's a network watcher, traffic analytics, and there's a new service in preview called network observability. This is purely for Kubernetes. It gives you the visibility at the traffic, even the packet levels, what sort of packet, how many packets is going from one end to another. Traffic analytics, that means that if two nodes are communicating each other, and there's a TLS handshake and those kind of things, it will summarize those, in the analytics it will summarize, it will say that node A communicated with node B 5 times, it sent these number of packets, and the time was that, this kind of stuff. Analytics, you will get that. Cluster level, you will have, you can get through the container insight, plus we have managed service for Kubernetes managed service. You can get that. Managed cluster level, the component, cluster insight plus resource logs. Similarly for Kubernetes objects, which are the deployment, stateful set, other stuff, managed service for premises or container insight, and the application is application insight. It's very rich. Application insight is just SDK that you enable with your application, just a NuGet package actually you do with your application and just provide this what's called key, application insight key. In the configuration, it will just enable it. It will start sending the metrics to your application insight. Now, on the right side, visualization. These are the tools. The visualization is you can use the managed Grafana. So when I say manage, it means that you don't have to deploy it. It's just a configuration, just turn on and do cluster, that's it. And some organizations, they do on their own, they deploy their Prometheus and Grafana resources of the cluster. But here, you can use the management. You can just turn on the feature, then you can use the manage feature. Or you can, in the visualization, you can visualize all of these things in Azure portal, which I'm going to show in a moment. So, Azure Monitor, it's an end-to-end service to monitor. It's not just limited to the Kubernetes, of course, but provide the monitoring specific for Kubernetes, but it's a bunch of, it's like an umbrella like this. It provides application level, OS level, Azure resources, subscription, tenant and resource level, custom resource level, and provide metrics and log, and you can visualize, get the insight on it, visualize, analyze, respond, and integrate. Respond in the form of alerts. You can do the alerts, or you can do action can perform the action in the form of auto scaling, or you can run the workbook and some of this stuff. Integrate with the logic apps or the export APIs, so you can take the action. So this is the Azure Monitor. Specifically for the Kubernetes, for AKS, it has like it collect the performance metrics, and at the container or sorry, cluster component level, it collects the event log, inventory, health, and container logs. All goes into using the Azure Monitor for container. What it collects is cluster inventory, events, event condition, container event logs, and performance, container performance. Very rich. Collects very rich metrics and logs. Just some of the UI snapshots here. So this is like Azure Monitor for container. Get detailed insight about your workload Azure Monitor. So you can see here in this snapshot, you can see this is the node level. You see the tab here, node. This is the node level. It shows you the average utilization, number of container running, average uptime running, percentage of utilization showing you. The next one is you can do at the cluster level. It shows the cluster health. At the controller level, you can see here different controller tab and information about different statuses of the controllers within your cluster. Plus, it goes further down. It goes to the container level. You can see here the fourth level. So container level is just the containers. CPU memory utilization of the container itself. So it goes to the different level. You see cluster level, it goes to node level, controller level, which is the Kubernetes own components, plus the container level. Log analytics workspace is like a central database of storing all the logs. All the logs go to the container log analytics workspace, and there's an agent which runs as a daemon set and sends these logs to the log analytics workspace. This is just showing how container inside works. We will touch base on that. It collects the container logs, AKS logs, operating system logs, and send to this for inside visualization and for responding or taking the action. Some of the dashboard of container insight. You can see this is for the container. You can see the percentile usage, number of container running, the node uptime, and this is about the action that you can perform for the alert. And this is the application insight. So application insight, you can see here, this provides the application performance indicator and metrics. So things here is it's showing the application map as well. So if the application is connecting to multiple applications, it shows the map of the application, it gives you the distributed tracing of the application, it gives the reliability, responsiveness, and here it shows you the outgoing request, ongoing request. It's very rich metrics about the application, it gives you application insight. And manage premises, like it's just another service getting very common as cloud native world or the CNC web project, of course, and there's a managed service available. And I go to the next one. Grafana is for the visualization. So this again managed service available, managed Grafana, which you can use to visualize all the matrices that gets collected by the container inside. And those one at the all 5 levels I'm talking about. So those 5 levels you saw, those 5 levels of metrics we can see in managed Grafana. Okay, so Istio Service Mesh, this is available as an add-on now. So as I it's in a public preview, and this is available as an add-on. Some of the organizations, they are doing their own Istio because it's open source, of course, Istio, but managing Istio is not easy. Some of the feature of Istio, traffic management, provides you traffic routing within the cluster, across the clusters, it provides circuit breaker, timeouts, different, it enables you to perform the A/B testing. It provides you the rich observability, of course, like one of the big feature of it, in the form of telemetry, communication of the services within the cluster. And it provides the security capability, which is like, help, it provides the, prevent the man-in-middle attack, mutual TLS between the pods, and you can enforce the policy using the Istio. So, and as I said, this is available as an add-on to the AKS as a managed service. So all customer have to do is when we create the cluster, they can just use that public preview feature, or if the cluster is already there, then you can just enable it as an add-on. Okay, so this is the last part, hopefully, your continuous delivery. I'm just touching base how to do the continuous delivery on AKS using the Azure services. So developer use the IDE as a Visual Studio to IDE such as Visual Studio to commit changes to GitHub. So what this is showing here is you use the GitHub, or the GitHub will kickstart the pipeline, DevOps pipeline. Azure DevOps, it will push the image to the container registry. And once it pushes that, then you will have the deployment pipeline, which will get the image from the container registry and it will deploy the pods within the cluster. At the bottom, it has you see the backend services, and the configuration of backend services will be defined within the config map or secret. So this is just showing continuous integration part. So DevOps part such as a continuous integration. You use Azure DevOps for the continuous integration. So this is just showing how you can configure. So here what I'm doing is, I'm doing the build an image. I have a two-step in here of CI. In Azure DevOps, I am building the image when I check in my code, building the image and pushing the image to the ACR using the Azure DevOps. And the second part of this is the delivery part. So I'm doing here is, I have a release pipeline. What it will do is, it will do the kubectl apply and deploy my configuration and deployment YAML into the container through the deployment pipeline. Okay, so this is just showing high level how can I do Microsoft deployment into the Kubernetes. So what it is saying is, when I do the build, I have a build number. So I will store that. When I create the image, I tag the image with that build number, and then I store that build number into the key vault. Then what I will do is, I will kickstart the release pipeline. The release pipeline will deploy the Helm chart, but before it deploy that, it get the build number from the key vault, substitute that as a regex expression, substitute that as a build number, and then once it does that, it will go and get that image with that build number and deploy to the container, deploy to the case cluster. So this is how it will work end to end. These are just a step. So the build number is used to nuclearify the build. Docker push to the container registry, store the build number to key vault, and the release pipeline will get the build number from the key vault. Use the regex task to just substitute the value to the YAML file and just do the deployment of the Helm chart. Okay, so what we have covered so far, let's summarize that. I think it's going to be a very long presentation.
we need to wrap up in about 5 minutes. So.
Yeah, so what we covered, we learned about the cloud architecture. Hope I conveyed the concept and you understood that, what the cloud architecture is. You understood the benefit of building cloud architecture. Hopefully you understood that. We discussed, we talk about high level what the AKS is, and we learned building the cloud architecture using the AKS. We learned the technique. So we applied the concept of building cloud native architecture into the AKS. Hopefully we have done that. And next part is how you can connect with me. So that's my LinkedIn link, this is my QR code, that's my email address. If you want to connect, you can scan the QR code, send me the friend request, and we can connect. And that's it.
And that's it. Thank you very much, sir. Fantastic. That is all about we have time for tonight, so we need to wrap up at 8. But thank you all for coming down. Really appreciate your attendance, and that was fantastic talk, super in depth, really covered like AKS from head to front. So yeah, fantastic. Thank you.